This is part 2 of my talk. We discuss the Alexandrov-Fenchel in hyperbolic space. We know that the hyperbolic space is a simply connected Riemann manifold with a constant negative sectional curvature -1. It has several models. The first one is the Poincare disk model. We identify the hyperbolic space as with the unit form equipped with the conformal metric ds square, which is given by 4 times dx squared over 1 minus x squared and to the square. We also have the hyperboloid model and the half-space model for the hyperbolic space. For the analysis of the curvature flows, we sometimes view the hyperbolic space as a vector product, which is a product of R plus with the unit sphere equipped with the metric dr squared plus sinh square r times the round metric. Now the question is to establish the Alexandrov-Fenchel type inequalities in the hyperbolic space. For that, we need to first recall the definition of Quermassintegrals. And for bounded domain omega in the hyperbolic space, the Quermassintegrals Wk of omega are defined by this equation. Here, this is a constant, and this is the integration over the space of k-dimensional totally geodesic subspaces, which may be equivalent to a gross manifold. And here the function chi is a characteristic function which is equal to 1 if the intersection of Lk with omega is non-empty and is 0 when the intersection is empty. This definition may not be good for the calculation, but for smooth domains, that is, if the domain has a smooth boundary, we can relate the Quermassintegrals Wk with the curvature integral. Firstly, we have W0 is just the volume, and W1 is the boundary area. And for higher order Quermassintegrals Wk plus 1, we can relate it to the integration of the K-mean curvature in K over the boundary minus the Wk minus 1. In the following, we always apply the curvature method, so we assume that the domain has a smooth boundary, and then the Quermassintegrals Wk can be related to the curvature integral by these equations. The Quermassintegrals in hyperbolic space have similar variational equations as in the Euclidean case. If we have a family of domains omega t whose boundary moves outward with speed f, then the time derivative of WL can be given by the integration of the speed function f times the L's mean curvature EL. This is the same variational equation as in the Euclidean case. So based on this, we can consider the volume and Quermassintegral preserving flow. The speed of the flow is this, which is the same one as in the Euclidean case. And here is the globator phi t. We chose it to preserve some Quermassintegrals. And we again have the monotonicity of Wk along the flow. So we have the monotonicity, and then we need to study the convergence of the flow. But however, for curvature flows in the hyperbolic space, there is some difficulties. One of these is that the convexity may not be preserved along the flow. Here, the convexity is equivalent to the principal curvature is positive. This difficulty arises from the evolution equation of the second fundamental form, which has some terms arising from the background geometry. For example, if we consider the volume-preserving mean curvature flow, then the second fundamental form HIG satisfies this evolution equation, and there is some term, some negative term, minus 2h times GIG. This term is a bad term for us to apply the tensor maximum principle. So we may need to assume a stronger assumption on the initial hypersurface to study the convergence of the flow. There is a natural convexity for hypersurfaces in hyperbolic space, the h-convexity. We give the definition here. A hypersurface M in the hyperbolic space is called h-convexity or horospherically convex if all principal curvatures I greater than 1. Equivalently, this means that for any point P on the hypersurface, there is a horosphere enclosing the hypersurface and touches at the point P. Let's look at the picture. If this is a pancreatic model of the hyperbolic space, and there is a bounded domain omega whose boundary is a smooth hypersurface M, then the hypersurface or the domain is called H-convex, is equivalent to that for any boundary point P, and there is a horosphere enclosing the domain and touches at the boundary point. Here the blue circle denotes the horosphere enclosing the domain omega. Note that the horospheres have principal curvatures equal to 1. So the domain has boundary whose principal curvature is greater than 1. If we assume that the initial domain has an h-convex boundary, then Guofang Wang and Chaoxia in 2014 studied the convergence of the following Quermassintegral preserving flow. And they showed that along the flow, the solution remains to be h-convex for positive time and converges to a geodesic ball when time goes to infinity. Note that this flow for k is 1 and L is 0 has also been studied in 2007. So now we have both the monotonicity and the convergence. Then we can compare the initial values of WL and WK with their limit values WLBR and WKBR, which are functions of the radius r. Now we obtain the following Alexandrov-Fenchel inequality. And for h-convex bounded and smooth domain omega in the hyperbolic space, we can compare WK of omega and WL of omega. Here for k greater than L. Here the function fk and fl are increasing functions defined as this for any positive r. The value of fkr is given by the wk of the geodesic ball of radius r. So now we have a complete family of Alexandrov-Fenchel inequalities for domains in the hyperbolic space, but the condition is h-convex, which is a strong condition. So we need to, we hope to weaken this assumption. The first result in this direction is the one proved by myself and Haizhong Li and Chang Wei Xiong for some spatial index, for precisely for k is 3 and L is 1. We can prove this inequality for two convex and star-shaped domains. And recently with Andrews and Chen, we proved this inequality for L is 0 and k greater than 0, and for for domains with boundary omega having positive sectional curvature. Here for hypersurfaces in hyperbolic space, the positive sectional curvature is equivalent to that the product of any two principal curvature is greater than 1. I will discuss this result in the following. And in the next year, Andrews and Hu and Li proved the inequality for k is n-1 and L is n-1 minus 2i for convex domains. Their method is by applying the harmonic mean curvature flow. And recently, Brendel, Guan, and Li proved the inequality for convex domains with k is n and L smaller than n, and for mean convex and star-shaped domains for k is 2 and L is 1. They introduced a new locally constrained curvature flow, which I will discuss in part 3 of my talk. Now the question is, can we prove the inequality for all k greater than L for k-1 convex and star-shaped domain? Now in the remaining time of this part, we discuss the result for hypersurfaces with positive sectional curvature. The theory is suppose we have a domain omega which is smooth bounded and its boundary omega has a positive sectional curvature. Then we can compare the wk of omega with w0 of omega. The method is again by applying the volume preserving curvature flow. That is, the flow is the same as the one considered by Wang and Xia. Here we consider the case for L is 0. The case step in the proof is the property that the positive sectional curvature can be preserved along the flow. I note that by the Gauss equation, hypersurface M in the hyperbolic space has the positive sectional curvature is equivalent to that the product of any two principal curvatures, kappa I, kappa G, greater than 1, because we can relate the sectional curvature of the space spanned by I, E, G by the product kappa I, kappa G minus 1. Here E, I is the principal direction corresponding to the principal curvature kappa I. In the following, I will sketch the proof of the preservation of the positive sectional curvature. For that, we consider this function capital G, which is defined in terms of the function x, the point x, and the time t, and frame O. The definition is that the function G is defined by h11 and h22 minus h12 square minus 1. Here h is the second fundamental form at the point x and time t. And the frame O is also normal with respect to the metric gxt. By assumption, this function is positive at the initial time. So to prove that G remains to be positive for later time, we apply the maximum principle. We consider a point x0 and t0 and a frame O0, which is given by E1 bar up to En bar, at which a due minimum of the function G is attained. This means that for any time t smaller than t0, and for all point x and for all frame O, the function g x t O is greater than g at x0, t0, and O0. By the minimum condition, we see that the first two directions E1 bar and E2 bar of the frame O0 and adjust the principal direction corresponding to the smallest two principal curvature, kappa 1 and kappa 2. at the point x0 and t0. Then we need to calculate the evolution equation of the function g. For the calculation, we denote f by the ek to the power 1 over k. First, the calculation of the evolution equation has two parts. First, we need to compute the time derivative, and second, we need the spatial derivatives. For the time derivative, we can fix the spatial point x0, and we note that the frame OT defined by this equation remains orthonormal with respect to g. Because we have this equation, because we can calculate that the metric g applied to EIEJ satisfies that its time derivative is given by this equation. The first term is the evolution of the metric applied to EIEJ, and we plus the second term and the third term, which is given by the definition of the free EI. And then we eventually get that this term vanishes. Then we have a family of free OT, which is also normal when time t varies. Then we can compute the time derivative of this function g. This function g now depends only on the time t, because here OT depends on t, and we fix the point x0. And we get that the time derivative of g when time t is equal to t0 is given by these terms. Here there are some terms on the time derivative of the second fundamental form. Then we need to calculate the spatial derivative. For the spatial derivative, we can fix the time t0, and to compute the spatial derivative along a direction nu, we can first find a geodesic gamma on the hypersurface starting from the point x0 and with respect to the direction nu. Along the geodesic, we can define a frame O depend on the parameter s, which is given by n direction E1s and ENS, which is also normal because we define this using this equation. Here the matrix gamma ij constant is a constant antisymmetric matrix. From this definition, we can easily check that the frame OS remains orthonormal along the geodesic gamma s. So now we have a function g of gamma s and fixed time t0 and the frame OS. Now this function depends only on the parameter s. And when s is 0, gamma 0 is just x0, and O0 is just the orthonormal frame O0. Because x0 and O0 is a minimum point, so the first derivative of this function g vanishes when s is 0. This gives an equation on the first covariant derivative of the second fundamental form. Here Laplace h11 means that the covariant derivative of h11 with respect to the direction nu. Then we can also compute the second derivative of the function g, which is non-negative by the minimum condition. By the calculation, the second derivative has some terms on the first two terms are second derivative terms of the second fundamental form, and there are some terms involving the matrix gamma and gamma square. Because the matrix gamma is arbitrary antisymmetric matrix, we can minimize the right-hand side of this equation and obtain this inequality. This inequality is an inequality for the second derivative of h11 and h22. Now we have two equations or inequalities. This term involves the second order derivative of h11 and h22, and from the time derivative, we have the time derivative of h22 and h11. From the evolution equation of the second fundamental form, this term and this term has some terms involving the second order derivatives of h11 and h22, which can be cancelled from these terms. So by direct calculation, we can and use some properties for the curvature function ek. We can obtain that the spatial minimum of the function capital G satisfies the following partial differential inequality. Partial T of G greater than minus a constant C times G plus some non-negative term. From this inequality, we can conclude that for G is positive for positive time T by applying the parabolic maximum principle. Now G positive is equivalent to that the evolving hypersurface has a positive sectional curvature. So this completes the proof of the case step. The positive sectional curvature is preserved along the flow. Here we can only prove this property for k greater than 0 and L is 0. For L greater than 0, we may not be able to prove this property. Now this is the end of part 2. In next part, we will discuss the locally constrained curvature flow in hyperbolic space that was introduced by Brendel and Guan and Li recently.